Welcome to Algebra 1, Chapter 7, Section 6, Exponential Functions. Let's do a quick review here, and I want you to circle each relationship that you believe is a function. Stop this video, attempt that, and go ahead and do the second one, cross out the equations that are not linear functions as well, then restart this video and see how you did. Let's see how you did. Okay, this is not a function. This is a function. This is not a function because the x repeats, and this is a function. And linear functions make up a line. So this is a function. This is not. This is a function. This is not. This one is a bit tricky right here. That is not a linear function. It is linear. It's a straight line. It's a straight vertical line, but it's not a function because the x is repeating. Our vocabulary is exponential. What is exponential? Well, it's a noun, and you can use exponential notation to write a repeated multiplication. So 8 times 8 times 8 times 8 is a base of 8 with an exponent of 4. Let's go ahead and use this vocabulary. In the expression 5 cubed, the 3 is called the exponent. When we have the expression 3 to the x power, that is an exponential expression. In column A are exponential expressions, and we're going to draw a line from column A to the equivalent expressions in column B. So 3 to the n to the negative 1. Well, remember, this negative here means reciprocal, so that matches 1 over 3n. Very similarly, if we look down here at 5n to the negative 2, we're going to use a reciprocal, so 1 over, and then 5 squared, n squared. Well, 5 squared is 25, n squared. When we look at 1/4 raised to the second power, we realize that that can equal 4 to the negative 2. This is n over 2 cubed. This is 2 cubed, n cubed. 2 cubed is 8. Our key concept in this video is exponential functions. An exponential function is a function in the form y equals a times b to the x power, where a is not equal to 0, b must be greater than 0, and it can't equal 1. X must also be a real number. So both of these are examples of exponential functions. This is exponential growth. This is exponential decay. If all the x values in a table have a constant difference, and all the y values have a constant ratio, then the table represents an exponential function. Looking at the table to the right, find the difference between the consecutive x values. In each case, we are adding 1. When we look at the y values, in each case, we're adding 2. So the ratio, there's really not a ratio because it'd have to be one over the other. The ratio is just a 1. There is a constant difference between the x values, and there is a constant difference, again, we're using the words difference here, between the y values. So this is a linear function. There is not a constant ratio between y values. If there was, it would be an exponential function, but there's not. So a linear function has the form y equals mx plus b. An exponential function has the form y equals a times b to the x. When looking at the rule y equals 3 times 6 to the x, it seems to represent an exponential function. In the rule y equals 3 times 6 to the x, the a would be 3 and the b would be 6. So does the rule y equal 3 times 6 to the x meet the definition of an exponential function? Is a not equal to 0? Check, that's true. Is b greater than 0? Check, that's true. Is b not equal to 1? Check, that's true. So yes, this is an exponential function. It meets the requirements. Let's take a look at problem number 2. So in this case, we have 20 rabbits and they triple each year. The function is f of x equals 20 times 3 to the x. And that gives a population over half-year periods. How many bunnies will there be after 3 years? Well, 3 years are 6 half periods. So f of x equals 20 times 3 to the x. The x is 6. That's the number of half periods. Evaluate the power is 729. And then we're going to multiply that by 20 and get 14,580. So there will be 14,580 bunnies after 3 years. Now we're going to graph some exponential functions. Now for many of these, you might simply have to plot some points and see how it looks. But as you can see, all exponential functions create this curve. And if you look at them, the positive and the negative, well, they're simply reflections over the x-axis. So if you can determine the positive values, you can determine the negatives by looking for that reflection. So looking at this first one, we're going to say when x is 0, y is 1, y is 1. When x is 1, y is 1/2. When x is negative 1, y is 2, because remember the negative means reciprocal. Let's see where that applies. So when x is 0, y is 1 applies to this one and this one. When x is positive, it got smaller. So this one goes away. Next positive. Let's try the next point. When x is negative 1, 2. So this is the graph that works for y equals 1/2 raised to the x. Now, the reciprocal, now when this becomes negative, you're looking for the reflection over the x-axis. So this graph right here is your reflection. So this is y equals negative 1/2 to the x. Let me erase this, and we'll take a moment. Maybe I can erase this. Now let's look at this graph and plot some points. When x is 0, y is 1, because everything raised to 0 power is 1. When x is 1, y is 2. When x is negative 1, y is 1/2. So as you can see, the negative value has a smaller value than the positive value. Let's see where that's applied. 0 is 1, is right here. 1 is 2, it's going up. Negative 1 is smaller. So this is your graph. So this is the graph y equals 2 to the x, which makes this a graph for y equals negative 2 to the x. In problem 18, we're going to complete the table, then graph each ordered pair and draw a smooth curve. Now obviously this is a bit more difficult, but very doable. So here we go. The first one, 2 times 9 is 18. So it makes the point negative 2 to the 18. Well, negative 2 to the 1/18, so put it about right here. It becomes a negative 1. 1/2 times 3, that'd be 1/6. So it becomes negative 1, 1/6, which would be about here. Third one, 0. Well, anything raised to 0 power is 1. That becomes 1/2. So it's 0, 1/2. My dot's not right quite on. And for the third one, we're going to have a 1. So it's 1/2 times 3. So it's going to be 3/2, which is 1 1/2. So that 1 is going to be 1 1/2. So our line is not going to cross 0, but it's going to look like this, as I sketched out. In this example, we are using the function 100 times 4 to the x. And we're going to create a table. So when x is 0, it's 4 to the 0, which equals 1, which is 100. So we need to plot 0, 100. 0, 100. When x is 1, it's 4 to the first, which is 4, which is 400. So 1, 400 is the point we're going to plot. X is 2, it's 4 squared, which is 16, which is 1600 I need to plot. So it's 2 to the 1600. When x is 3, it's 4 to the third. 4 to the third is 64, which is 6400 I need to plot. That makes my point, and 3 to 6400 comes up to here. Now when it's the fourth, 4 to the fourth is going to be 256, so it's 25,600. So the point is 4, 25,600. And of course, at 4, we're up to right about here. Now, in this case, we are not going to connect the points to the graph. So this is simply what we have. Please go ahead and do the lesson check and bring any questions you have to class tomorrow.